Hi everyone, welcome to the webinar. My name is Clarisse. I work here at IB Web in marketing and will be your host for today. So today's webinar is the second part of a two-part webinar series on 5G, which will focus on beamforming in 5G, and I'm joined by Ali Jemmali to cover this topic. So just before we get started, I want to cover a couple housekeeping items. So webinar will be recorded and sent to everyone after the presentation. And also, please feel free to ask questions to our presenter by using the GoToWebinar question box. So now everyone is ready. I'm going to hand the microphone off to Ali. Hi, Ali. Thanks for being with us today.
Hi, Clarisse, and thank you for the introduction, Clarisse. Hello, everyone. Good morning, good afternoon, and good evening, depending on where you are. And welcome to this second part of our 5G webinar series. My name is Ali Jemmali, and I am a RAN research engineer at IBWave. I'm really glad and delighted to host this webinar and to share with you some knowledge about 5G new radio technology. In this part of the webinar, we are going to talk about, in my opinion, one of the main key aspects and the most relevant concept in 5G new radio, which is actually the beamforming techniques. So let's have a brief look at the agenda and the outline of this webinar. So I will start with a small background and motivation behind using the beamforming techniques in 5G new radio. Then I will continue with the principle in general of beamforming generation using antenna array. And then I will carry on with the discussion on different types of implementation of beamforming. So we will discuss the difference between analog, digital, and hybrid beamforming. Then we will tackle the beamforming, how it is specifically applied in 5G new radio standard. And finally, we will go briefly about the key modeling aspect of beamforming and multi-beam antenna in our IBWave design tool. So let's start with what we have already learned from the first part of the webinar. So it was mentioned that there are two frequency ranges defined for 5G new radio, namely the frequency range 1 and the frequency range 2. The frequency range 1 is basically a sub 6 GHz frequency range, and it is not that different from what we have already been using in the previous 4G or former wireless cellular technology, except maybe the part of 3.5 GHz, which is mainly a CBRS band. However, the frequency range 2 is completely different, and it is completely new for wireless cellular technology. The frequency range 2 is mainly a very high frequency band where the wavelength is very small with respect to frequency range 1. And the problem with this frequency range 2 is that it comes with many challenges with respect to frequency range 1, because they are very different. And when we talk about different frequency range or different frequency band, we should talk about the channel characterization of these bands and how they are different. And in general, in radio propagation is normally characterized by two different phenomena. So the large scale fading and the small scale fading. The large scale fading includes the median path loss, as well as the shadowing effect of the component of the channel. And for the small scale fading, it represents actually the multipath components of the channel. So in terms of large scale fading, the frequency range 2, because of high frequency and because of smaller wavelength, and because of based on Friis equation, the path loss is found to be significantly high at frequency range 2. Also, the material transmission loss and blockage also is found to be significantly high at frequency range 2. In terms of small scale fading, also the frequency range 2 behave completely different to frequency range 1. In frequency range 1, it is known that the multipath component of the channel is very rich. However, for frequency range 2, and because less possible reflections and poor diffraction, the multipath component of frequency range 2 is found to be very poor. This poor behavior of multipath component at frequency range 2 will not make the MIMO performance as good as it is in frequency range 1. The MIMO performs well when the channel has some kind of rich scattering effect and where the channel matrix has a high rank indicator. So then the problem, the question, the legitimate question, why are we moving to this high frequency band? Why do we need such frequency band? And the answer is all actually about the bandwidth. We know in LTE, the maximum channel bandwidth is defined to be 20 megahertz. And the carrier aggregation was defined to improve the data rate and the throughput of the system of 4G. And there is a maximum of 5 carrier aggregation can be applied in 4G. So 5 carrier aggregation with 20 megahertz each, we will end up with a total of 100 megahertz of the channel bandwidth. However, in practice, not all operators would have this 520 megahertz channel. We may have in practice maybe 3 or up to 4 channels of 20 megahertz, which is maximum of 60 or 80 megahertz. But in 5G, one of the requirements for 5G in terms of enhanced broadband application is to be able to provide a data throughput of up to 1 gigabit per second or up to 10 gigabit per second in each initial deployment. And the only way to meet this requirement is only to have more bandwidth. And it is found that only in the frequency, millimeter wave frequency band, they can offer this such broadband spectrum. So we know that for 5G, the maximum bandwidth was defined to be 400 megahertz. So if we consider a carrier aggregation of 5 carriers, we may end up with a total channel bandwidth of up to 2 gigahertz, which is a very high spectrum. In addition to this abundance and disposal of broad spectrum in 5G millimeter wave, there are also some benefits using this millimeter wave frequency. For instance, there is a possibility of frequency reuse within a shorter distance, and this is because of high attenuation loss. So this will allow us to create high density networks, and this will increase the capacity of your system. Another benefit of using this millimeter wave frequency is the possibility of designing compact massive antenna array. And this is because of a smaller wavelength. And this will help us implement the technique of massive MIMO deployment. Another benefit of using this millimeter wave frequency is what it is called the better interference management. And this is possible because in millimeter wave, we can create a very narrow beam width, and this will help better manage the interference between users, or maybe the interference also between different node Bs. So then how to deal with the problem of millimeter wave, which is the high load path loss calculation. And for this, let's have a look at a simple scenario deployment of wireless technology. And let's suppose we are going to deploy 2 different systems, one at the sub 6 gigahertz and one system at the millimeter wave band. And let's suppose, for comparing apple to apple, let's suppose that these 2 systems use both single antenna, and they have both the same EIRP output power. It is clear that based on this configuration, the propagation and the coverage of the sub 6 gigahertz will be much higher than the millimeter wave. And this is because of high attenuation loss at millimeter wave. However, thanks to the antenna theory, if we apply some kind of focusing the energy of millimeter wave using some kind of special antenna, we can actually increase the gain of the antenna, and we can also reach the coverage of the sub 6 gigahertz. So This technique of focusing the energy into one particular direction, this is what we call beamforming. So in other words, we can say that beamforming is a technique to focus the received or the transmitted energy into one particular direction. Here it should be noted that this beamforming, it's not really new for 5G. These techniques of beamforming has been used for decades now, but in different wireless applications, such as radar application, satellite communication, and other applications. So now let's see how to create and how to generate this type of concentrated beam and concentrated energy. And for this, in practical, normally we may have different type of antenna that can generate this type of beamforming radiation pattern. For instance, there is the so-called horn antenna, which are mainly used in radio measurement, or they can be as a point for reflectors of antenna. There is also the parabolic antenna, which are widely used in the satellite communication, in radar communication. And also there is a third type of antenna, which are Yagi antenna. Also, this kind of antenna can concentrate the received energy or the transmitted energy in one particular direction to improve the beamforming. However, all these mentioned antenna types cannot really be applied for wireless cellular technology, because cellular technology is mainly has a high degree of mobility, and we should somehow be able to steer the beam format or to change the beam for different direction depending on the user location. So all these three type of antenna cannot really be used for wireless technology. But fortunately, there is another type of antenna from antenna theory, which are called antenna arrays, which are a very practical case for wireless technology. So what is antenna array? As a simple definition, antenna array is a set of several antenna elements arranged in a space and interconnected to produce a directional radiation pattern. And here I'm showing different types of antenna array. And the one shown on the left side of this slide is just to illustrate the principle of operation of this kind of antenna array. So if it is deployed in the transmission mode, so your source, your RF source should be applied to some power divider to split the power between each antenna element. In addition to that, if we want to have more control on the beam, on the generated beam, we can add some phase attenuator between each antenna element and also amplitude attenuator and phase shifter instead. So if it is deployed in the receiver mode, so instead of having this power divider, you should have some kind of combiners to combine all the received signal from all the received antenna element and then fed this received power to the receiver. On the right side of this slide, we show two typical antenna arrays that are widely used in the industry. For instance, there is what it is called linear antenna array. This is an antenna array where the antenna elements are arranged in a straight line. There is also another type, widely used type of antenna array, which is a two-dimensional antenna array, where the antenna elements are arranged in a two dimension, in horizontal and in the vertical. In addition to this, if the distance between the antenna element is uniform, so then we call this type of antenna uniform linear antenna array or uniform rectangular antenna array. So this is widely used in the industry. Now let's see how this antenna array can focus and can generate this type of focused beams. For this, let's have a look at one simple example using one antenna element, which is, let's say, a simple case of cosine antenna, which is shown on the left side of this slide. So the radiation pattern of this type of cosine antenna, it has the shape of cosine, that's why it is called cosine, and it has a wider beam on this plan. So what happens if we add more antenna element in straight line? For instance, what we see in the middle of this slide, when we add more antenna for 4 antenna element, we can notice, and it can be demonstrated from mathematical modeling, that this beam will be narrow, and we also can notice that there is one beam, side beam that level that it was created. So when we increase further the number of antenna element, for instance, if we increase this to 10 antenna element, this is what it is shown on the right side of this slide. So it is clear that the beam width is becoming narrow, and the number of side lobes are now much bigger, and the side lobe will be high. But this is a physical problem of the antenna array, but fortunately there are some kind of techniques to reduce these side lobes and to reduce the level of these side lobes. One other particular characteristic of this type of antenna array is the possibility of steering the angle of your generated beam. And this is because of the possibility of making phase shifting between the antenna element. So in this case, the angle of the steering of this beam will depend on the phase shift between the antenna element. And this principle of angle steering of the beam can be illustrated with the following figure. So let's see on the left side of this slide, let's suppose we have a simple antenna array with 2 antenna elements. For instance, antenna element 1 and antenna element 2. And let's suppose we have a received plan wave, which is traveling toward this antenna array, which has 2 antenna elements. The plan wave is represented here with the green dashed line. It is clear from this figure that the plan wave will reach first the antenna element 2, and then it has to travel some other distance, difference distance, to reach the antenna element 1. This difference in distance, it can be easily calculated using trigonometry equations, and it can be found that this difference distance is a function of the distance between the antenna element and a function of the angle of arrival of this plan wave. So as we know in propagation, the difference in distance will be reflected in some difference in phase between these 2 plan waves at antenna element 1 and antenna element 2. And this difference in phase is shown here on the top as the phi equal depends on the propagation constant of the wavelength, and this difference distance, which is the sinus theta. So this principle with respect to the received plan wave, but we know that the antenna is reciprocal properties, which means that it can operate the same way in the receiver, or the main characteristic will be applied for the transmission mode. So in transmission mode, if we apply this kind of phase shift between the antenna element, for each antenna element, we can create what it is called the array response vector or steering vector to this all antenna element. We can actually easily create this beam oriented with some steering angle, which is the theta angle that the calculation of the phase shift was based on. So this is one of the main key characteristics why this type of antenna are widely used and are more practical for wireless communication industry. So now to have an idea how this antenna array can be modeled and how this radiation pattern can be calculated, the principle, without going in more details of mathematical modeling of all this aspect, but the simple principle is called the pattern multiplication. And what is pattern multiplication? Is simply we have to know the pattern of a single antenna element. Let's say if it is a half dipole antenna or if it is cosine antenna. So we should have the pattern of this particular antenna element. And then we have to calculate the array factor, which will depend on the geometrical arrangement of your antenna array. For instance, it will depend on the number of elements, how many antenna elements you would use. It will depend, as we have seen, on the relative amplitude difference between the antenna element, also on the relative phases between the antenna element, as well as their spacing, the spacing between the antenna element. So having all this calculated, you can easily calculate your beamformed signal or beamformed radiation pattern as a multiplication of the single antenna element and with the array factor. Here, I wanted to mention some key parameters that will affect your antenna array, that will affect the shape, it will affect your beam width, it will affect the gain of your antenna. So in principle, there are two main parameters that will affect your beamforming. For instance, the first parameter will be the number of antenna elements. We have seen in the previous example that as we increase the number of antenna elements, the beam width becomes narrow, and this will increase at the same time your gain of your beamforming gain. The other parameter that will affect your radiation pattern is the distance between antenna elements. And this parameter in general, it will affect the level of your side lobes. And the last parameter that will affect actually both at the same time, it will affect the side lobe and the beam width, is the current distribution between the antenna element. So we can apply what it is called uniform current distribution, which means all antenna element will receive the same level of power, or we can apply some current distribution in order to improve the side lobes or to improve the beam width of the antenna. And from antenna theory, it can be shown that these two parameters are inversely related, which means that if you increase the side lobes, it will increase the beam width. And if you want a narrow beam width, so then the side lobe will be affected inversely. Here I wanted to show you some modeling or simulation result of this type of antenna array with different steering angles. For instance, here I have done some simulation using steering angle from 0 to 60. And I wanted to show how this radiation pattern will be affected as a function of your steering angle. If we look at the 0 steering angle, which is almost symmetrical radiation pattern, then because of the physical of this radiation pattern, so the radiation pattern at 60, it will be much wider than the pattern of 0 degree. The blue radiation pattern is with respect to 0 degree, and the light blue radiation pattern is with respect to when the steering angle is 60 degree. You can note easily how this radiation pattern is now wider and how it is not almost symmetrical between this angle of 60 degree. This is very important aspect of antenna array. Now let's talk a little bit about the implementation aspect of this beamforming application. And let's see what are the different beamforming types. We know that in any wireless communication systems, the system can be implemented in two different components, which are mainly the digital signal, and we have also the part of RF signal. And depending on where you want to implement all this weighting factor to your antenna element, you may have two different options for this case. The first one, if you apply all this weighting factor in the analog domain or in the RF domain, so this is what it is called analog beamforming. However, you can also, because you have this part of digital signal processing, you can implement all these weighting factors to the signal in the digital domain. And in this case, you will have what it is called digital beamforming. And if you want, if you can also implement one part of these weighting factor in digital domain, you can also apply another part in the analog domain. In this case, you will have what it is called hybrid beamforming. So it is a combination of analog, some part of analog, and some part it is digital implementation of beamforming. And let's have a look at this type of beamforming in more details. So for analog beamforming, we mentioned that this weighting factor should be applied in the analog domain, which is after your RF chain, which is RF signal. And by what we mean by RF chain is all the components that are needed to create your RF signal. For instance, RF chain should include the digital to analog converters, the up converters, the amplifier, the filters. All this type will be included in this RF chain. And one RF chain should be split, the same signals should be split between different antenna element, and for each antenna element, we can apply some phase shifters and some amplitude attenuators to have the desired radiation pattern. Of course, like any implementation, there is some advantages and some disadvantages for such implementation. And the advantage of analog beamforming is really the low cost, because this phase attenuator and the RF frequency are not too cost, and it is easily to implement. So it is not very costly to implement this kind of beamforming. The other advantage of using analog beamforming is really the low complexity, because it is very simple. You just have one RF channel. You just split this signal between different elements and then apply all this splitted signal to each antenna. Another advantage of analog beamforming is really the low power consumption, because you have only one RF chain, so you don't need a lot of power, and this is an advantage of applying analog beamforming. However, there is few disadvantages of using this type of beamforming, and the main one is because we have only one RF chain, so we can only make only one single beam, because there is only one RF chain. The other disadvantage of this analog beamforming is really the high inter-user interference, because it is high to manage this side lobe in this analog domain. That's why you will have more side lobes, and the level of side lobes will be much higher. It's not like in digital when we can easily manage all these coefficients. So now let's see what is the difference with digital beamforming. So with digital beamforming, we have to do all this processing at the baseband and apply all this beamforming coefficient in the baseband. So because in baseband we can process different signals, so we can have multiple signal, which is the number of streams that would be transmitted, and apply all this processing to each stream separately. And then we can, the output of this will be for each antenna element would be one RF chain should be applied to create this beamforming radiation pattern. So the number of this antenna element will be exactly equal to the number of RF chain that you would need to apply to implement this digital beamforming. So what is the advantage of this type of implementation? Of course, because we are doing all the processing in the baseband and it is easier to do this kind of manipulation, it is optimal. It may provide optimal performance of this beamforming. You can easily control all your beamforming pattern. Also, another important advantage of this type of digital beamforming is you can generate multiple beams because you have different special stream, you have different RF chain. So normally you can create different beams simultaneously. And another advantage is really the high degree of freedom. So because you are manipulating in the baseband, so it is very easy to do all this calculation in the baseband. However, there are of course, some disadvantages of such implementation. One of the main disadvantage is really the implementation complexity. Now, because you have different RF chains, so you should calibrate all this RF chain. You should make sure all these RF chain are working on the same different antennas, and it is very complex to manage all this at the same time. Another disadvantage of this type of digital beamforming is the high power consumption, because now you have high number of RF chain. So of course, each RF chain will consume its own power. So you will add this power consumption as the number of RF chain is increased. And of course, this will include the design cost to be higher as well. Now, if we want to use the advantage of the digital beamforming and the advantage of the analog beamforming, there is another type which is hybrid beamforming, which combine the two different beamforming types. And in this case, for hybrid beamforming, it's kind of going through three different levels of this beamforming. The first one, what you see on the left side, is the number of your special stream or the number of signal you want to transmit. And then you have the number of RF chain after baseband processing and before applying analog beamforming. And here is the main point for hybrid beamforming. The hybrid beamforming the goal is really to reduce this number of RF chain that we have seen in the digital beamforming, to reduce the complexity. And after this RF chain, of course, you have all this analog beamforming, and the antenna element of your antenna array should be, of course, greater than the number of RF chain. And here there is two possibilities of deploying such hybrid beamforming. The first possibility is if for each RF chain you connect to sub antenna element, not all antenna element. And in this case, you will have what it is called a sub-connected hybrid beamforming, because you are not connecting all the antenna element for each RF chain. The other possibility is what it is called fully connected hybrid beamforming. So in this case, this is what you see on the right side of this slide. So you can notice that each RF chain is connected to all antenna element. So now it is clear that this implementation, it will have more degree of variability with respect to your radiation pattern, because you are using all this antenna element. So of course, the fully connected hybrid beamforming will be much complicated to implement, but with respect to performance, it will be more performant with respect to sub-connected hybrid beamforming. And in the industry, what we have seen so far, it's more this type of application, especially in the massive antenna array, where you have a very high number of antenna elements. Imagine that you have 8x8 antenna array with cross-polarized antenna, which will be almost 64 and 128 antenna element. Imagine that you would need in poorly digital implementation, you would need 128 RF chain for each antenna element, which is very complex to accomplish and to implement. So to summarize the beamforming types, you can find also maybe different classification, but in general, this is the main classification of beamforming type, as we have seen. So in general, there is the analog and digital beamforming. You can combine these two types of beamforming. You can implement hybrid beamforming. And for hybrid beamforming, we have seen that there are two possibilities. One with fully connected hybrid beamforming and one with sub-connected hybrid beamforming. Here, I wanted just to mention to add one more beamforming type, which is related to analog beamforming, because you may heard of this type of analog beamforming, and I think it is still widely used, especially in hybrid beamforming, because you still have this part of analog beamforming. I think the most used analog beamforming is Butler matrix, and there is another type I didn't mention here is blast matrix also. They have also their advantage and disadvantage, but they are still widely used in the implementation of beamforming techniques. So now let's go to deal with the beamforming, how it is specifically implemented in 5G New Radio. All what we have mentioned so far, it's general concept and general aspect of beamforming, but let's see how all these aspects are implemented in 5G. But before that, we should mention that this beamforming, it's not really new in 5G. Actually, in 4G, there are some basic concept of beamforming that was already defined in 4G. So let's go briefly through this type of beamforming aspect in 4G. It is known that MIMO is a fundamental component in 4G, and there are different MIMO operation mode defined for 4G. These MIMO operation mode are known in the standard as the transmission modes. In release 8, there were almost 7 transmission modes defined for 4G LTE standard. The transmission modes 1 to transmission mode 6 are mainly SISO transmission, diversity, and the spatial multiplexing, including the open loop spatial multiplexing and the closed loop spatial multiplexing. The only transmission mode which supported the beamforming is the transmission mode 7. And it is called single layer beamforming, and it uses the antenna port 5 in 4G LTE standard. However, we should mention that this beamforming in the 4G and this transmission mode 7 is not really beamforming based on the direction of the radiation pattern of focusing the beam. It is most based on the channel estimation of the UE. And it is more called precoding than the beamforming. So what is the difference between beamforming and precoding? Precoding actually is a general technique to apply some weighting factor to your transmitted signal in order to facilitate and improve the receive signal. It can also improve your SNR, signal to noise interference ratio at the receiver. And beamforming is actually a special case of precoding. So beamforming is a precoding where the weighting factor of the antenna for the antenna will produce this kind of focused radiation pattern. So that's the difference. In release 9 of 4G, the beamforming was enhanced with another transmission mode, which is transmission mode 8. And this transmission mode 8, it is called dual layer beamforming. With dual layer beamforming, we can send actually 2 beamformed signals to one particular user, which is a MIMO user, or we can also send one beamformed signal to one user and another beamformed signal to another user. This is the so-called beamforming and multi-user MIMO application. In release 10, the beamforming was further enhanced with the transmission mode 9. And transmission mode 9 is simply a single user beamforming, but the new thing here is that it is used with up to 8x8 MIMO configuration. So now let's see how this beamforming is applied for 5G. And it is clear that in 5G, the beamforming is more developed in 5G, mainly because of these millimeter frequencies. And let's recall what we have learned from the first webinar. We mentioned that there are different signals and different channels in 5G new radio. It's like in LTE, but there are some different in the signals and channels. So the signals normally are created at the physical layer. What you see here on the right side of this slide, so you see the radio protocol layers, and the signals are physical signals that are created at the physical layer, which means that there is no data coming from the upper layers, like from MAC or RLC layer. So they are simply created on this physical layer. And the type of new radio signal that are defined for 5G are mainly the synchronization signals, which are primary and secondary. So it is like in LTE. And there are also few other signals that are defined like the modulation reference signal, which are mainly used for the demodulation with different type of channel. It can be used for traffic channel. It can be used for broadcasting channel. And there is also what it is called phase tracking reference signal, are used for the tracking of the phase. There is also the channel state information, which are mainly used to estimate the channel and to help decoding the received signal. However, for the channels, normally the channels carry more data from the upper layers. So it could be control data, it could be user data. So for instance, the physical broadcasting channel will carry some broadcasting information from upper layers. The physical downlink control channel will carry some data from the upper layer with the control for the control of the UEs. And there is also the specific data channel, which is PDSCH, which is used for specific user for data transmission. So the synchronization signal and the broadcast channel are put together to form what it is called a block of signal and channel, called it SS block. So this SS block is sent over 4 OFDM symbols, as shown here in the figure, in the time domain, and over 20 resource block in the frequency domain. So to enable the beam sweeping of these SS blocks and the the broadcast channel, the transmission of this SS block is organized in a periodical series of SS, what it is called SS burst set. So the number of this SS block in one set depends on the frequency of operation. So the table, the above table, which is under SSB pattern, shows the maximum number of SS block in SSB burst. So for instance, we should remind these numbers for sub 3 gigahertz, the maximum number of SSB that we can send is 4. For frequencies between 3 and 6 gigahertz, the maximum number is 8. And for millimeter wave, the maximum number can be up to 64. We should mention here that it is not exactly always we should send the maximum number of this SSB pattern. Sometimes we may send less than what it is mentioned here just to reduce the overhead. And the table below shows this SSB periodicity. So this SS bursts are sent with some periodicity, and this is the possibility of periodicity with respect to SSB burst. So how this will look like in real radio frame. So what you see here is a sample of radio frame, and you can see that this SS bursts are confined within 5 milliseconds, which is half radio frame. And if we take the example of sub 3 gigahertz, we may have only 4 SSBs, and this SSB can be in 5G can be sent with different beams. All this SSB has its own index, so the receiver will know what is the beam for each SSB. And this is illustrated in this kind of figure. The implementation of this is like when you can consider that all these beams are transmitted in sequence time. So for instance, let's suppose that the beam 1 is transmitted. So the UE1 will receive this beam and the UE2 also will receive this beam, but both, because they are not on the same orientation of the beam, so this will be a very low signal with respect to both UEs. Now, when the beam 2 is transmitted, the UE1 will receive a high signal because it is on the direction of this beam. However, the UE2 will not receive a high signal, will receive a weak signal because it's not on the direction of UE2. So the same principle will be applied for UE2. The highest beam will be received by UE2 SSB4 with some index, and UE1 will receive the maximum received beam will be beam 2. This is in general the general concept of beam sweeping in 5G, how it works. So the UE can measure all these beams and can feed back the measurement to the UE to the node B to know in which almost direction the UE is. So now let's talk about some application of this antenna array in 5G. We find a lot of this, what it is called cross-polarized antenna array, which is mainly a two-dimensional antenna array with cross-polarized antenna. So we may have this plus 45 antenna element, and we may have this minus 45 antenna element. And we can create with this two different set of antenna element, two different beams, one with plus 45 and one with minus 45. This plus 45 is referred to the antenna element, and it's not referred to the direction of the beam. There is another possibility of using this antenna array is to subdivide this antenna array to two sections or sub-panel, and you can create two other beams with the upper subarray and with two other beams with the lower up subarray. And in this case, you can generate 4 beams. You can apply this for MIMO 4x4. Now, for the difference between the beams with different channels, we have seen that the number of maximum SSB for, let's say, for the sub 3 gigahertz is 4. So we can use a wider beam to send this kind of SSBs. But when it comes to the PDSCH, when it comes to the transmission of specific data, we can use a narrow beam and we can use the all 16 by 16 antenna array instead of sub-array of 8 by 8. So with 8 by 8, you will have a wider beam. With 16 by 16, you will have a narrow beam, and you can use this to transmit the traffic channel. Another application or another illustration of this type of antenna array used in the industry is you can, let's suppose you have this type of antenna, which is mainly 8 by 8 cross-polarized antenna, which means you have 64 by 2, which is 128 antenna element. And let's suppose that there is a possibility to connect each column or each row with one particular RF chain. So in total, you may implement 8 RF chain. This 8 RF chain, if you apply this kind of hybrid beamforming and digital beamforming, so it can be possible to create 8 possible beams at the same time. And when we have 8 possible beams, we can actually serve 8 possible UE if they are well separated in the space. So this is one of the applications of such cross-polarized antenna and beamforming. Now let's talk briefly about the beamforming and the key modeling aspect in IBF design. So in IBWave design, we made some generic antenna array, and we can use this generic antenna to do some simulation and to do some prediction using this type of antenna array. So for instance, here I'm showing one example that we generated for this generic antenna, which is a 16 by 16 antenna array. And from simulation, it is found that this antenna array have an antenna gain of almost 27 dBi and the beam width of 9 degrees in the horizontal and the vertical plane, because it is a symmetrical antenna 16 by 16. So it may have this symmetrical radiation pattern in both planes. Here also the element spacing between this in this antenna array is half lambda. And the frequency, this is for 28 gigahertz. So how we can use all these generic beam generated? So if the beam, if we want to cover this in the horizontal plane 120 degree, then we should create some kind of 13 beams to cover all this horizontal plane of 120 degrees. In the vertical plane, if we want to cover 45 degrees, then we would need 5 beams in the vertical plane. So in total, you would have 65 beams, and you can create this combined beam of the antenna, and you can run prediction using all these antenna, generic antenna. And in IBWave, you can create a multi-beam antenna with different number of beams. In this particular case, I am showing this antenna of 65 beams, and you can assign different beam to different antenna port of the antenna. And then you can run this prediction with using all the beam, which is combined beam, or using particular beam. And here I'm showing two prediction, one with the single beam on the left side and one with the multi-beam prediction, which is all combined beams, if you want to see what is the coverage if all these beams are available at the same time. And here just one small concept of this SSB, how it can be assigned to different pattern. So for example, if we have 3 SSB indexes, so we can assign for SSB1 one particular radiation pattern in one particular direction. We can assign the beam 2 to a different radiation pattern, different steering angle, and we can do the same thing for SSB3. So this concludes my presentation, and I'm ready for the question if we have some time for a question, Clarice.
Yeah, thank you, Ali, very much for this presentation. We have a few questions from the audience.
Yes.
The first question I have for you is, can beamforming antennas be used in a 4G or LTE environment?
Yes, actually, that's what we covered a little bit. So we mentioned that the 4G has some basic beamforming concept already defined in some different modes. Specifically, we mentioned that in the first release, release 8, the transmission mode 7 was basically beamforming, which is called single layer beamforming. But the only point is what I mentioned before is that it is not really beamforming based on the radiation pattern of the antenna. It is most based on the pre-coding, which is based on the channel estimation. And we mentioned what is the difference between pre-coding and beamforming. But the overall answer, yes, there are some basic beamforming techniques which were applied already in 5G and 4G. Sorry.
Okay, thank you. Regarding the session 1, so we talked about analog and digital beamforming, and
Yes.
someone is asking which is best, and do you know what the OEM vendors are supporting, both or one or the other?
Well, what we have seen so far is mostly hybrid beamforming implementation. As we mentioned, the digital beamforming is really difficult if you have a high number of antenna elements. So suppose that you have 8 by 8 with the cross-polarized antenna, so you will end up with 128 antenna element. And if you really want to implement fully digital beamforming, you would need 128 RF chain, which is very complex to implement. So in practice, we have seen more hybrid beamforming, but it can be implemented for small RF chain. The digital beamforming can be implemented.
Okay, thank you. Next question, is hybrid beamforming possible in 5G with massive MIMO, and what are its advantages?
Yes, actually, if you deploy hybrid beamforming with the option of fully connected, and if you use a high massive antenna, yes, you can still apply the massive MIMO implementation, but of course, the performance will not be as purely digital implementation. But still, with the hybrid fully connected, you can still use all this antenna and this RF chain to create different signal for different users and focus them to different orientation. And you can definitely apply the massive MIMO concept of 5G.
Okay, great. What is the directivity of the beams formed for 5G, and how many can be formed simultaneously?
Okay, the gain of the antenna array is really, it depends really on the number of antenna element. We have seen in the presentation that as we increase the number of antenna element, the beam width will become narrow, and this will increase your antenna gain. So as you increase the number of antenna element, you will increase your gain basically. As for the number of simultaneous beams, it really depends also on the number of RF chain that you are using. And in theory, from digital beamforming, it really depends actually on the analog to digital and digital to analog conversion. But in practice, you can create many different beams in digital than in hybrid beamforming.
All right, thanks. Next question is, how many radiating elements are in the typical antenna arrays?
So far, we have seen this 8 by 8 with the cross-polarized antenna, which is mainly 64 with cross-polarized, which is in total 128 antenna element. We also have seen some kind of 16 by 16, but it is not really for real deployment, maybe for kind of measurement or investigation of beamforming transmission in 5G new radio.
Okay, so I think we're going to go with one last question for today. So the question is, can beamforming track user location, and how can this be modeled?
Yes, actually, if we recall how these SSB are transmitted and how these SSB are transmitted from different beams and different orientation of the beam, this kind of implementation help finding the location of your UE. So we mentioned that the UE will measure all these beams transmitted from the node B, and each beam will have its own index. So the UE will measure all these beams, and it will it will feed back all this transmission to the node B in the case that it will indicate what is the beam that it is maximum for this UE, and this actually will reflect your orientation with your location with respect to this node B. Each beam has its own index, so each index will have a specific angle or steering angle, so it will help defining the location of your UE.
All right, very interesting. So, well, thank you very much, Ali. I'm sure everyone has now a clear vision of beamforming in 5G. And I would like to thank you also attendees for joining us today. And I hope to see you at the next webinars.
Thank you everyone for listening. Thank you, Clarice.
Thank you. Bye. Bye.
Bye.